Good morning, class. This is Mr. Barris. I am currently evacuated from my house in Florida due to Hurricane Dorian, which is quickly approaching my town. And so for that reason, I will try my best to be there for class tomorrow and on Wednesday. But if I cannot make it due to my internet being down or to me not being able to get back to my house, I apologize. I am posting this video in advance just so that you have some instruction, just in case I cannot make it. Thank you to those who have started the course already with the student orientation and in topic 1. Those of you who have not had a chance to do so, please do so quickly. In the past week since I posted my intro video, I've gotten a couple emails, mostly just asking for clarification on due dates and what to be doing, what you should be doing during this first week. So let me just clarify that. So remember, this first week, now that I am going to be presenting topic 1's material to you, you have 1 week from your Zoom session with me, which should be taking place on Tuesday and Wednesday this week for the regular and the honor sections. So you have 1 week from our Zoom session to turn in the material for topic 1. I believe there are 4 assignments, a quiz, and a discussion to turn in, all by our next Zoom session, which is next week. Okay, so let me clarify that even more by bringing up my calendar. So by bringing up the calendar, you can see that today is Monday, the 2nd of September. I believe our Zoom sessions scheduled for this week are tomorrow, the 3rd, and Wednesday, the 4th, for the honors class and for the regular class. So suppose for a second that you had class tomorrow with me on Zoom, Tuesday, September 3rd. Okay. If you had class on the 3rd and we were presenting topic 1 in that Zoom session, I would expect you to have topic 1's material done the week following. That would be the 10th by the end of the day. Okay. And it's not going to be a lot of work to do. We're going to be going over the assignments that I'm expecting you to have finished next week today. So just keep that in mind. You have a 1 week window to turn topic 1's material in before it will be counted late. So let's talk about topic 1. So if you go to your course, I'm in the honors course right now. The regular course is pretty much the same thing. So let's go ahead and get into our class. So suppose I'm going into the honors course. And I'm going to be talking to you tonight about topic 1. So if I click on topic 1, I can see all of these assignments, readings, discussions, quizzes to get done by the end of next week. Or by next week, I should say. Okay, so I'm going to ask you to read in advance of the Zoom session so that you can have questions prepared if you have them. Otherwise, it will be tough for you to keep up if you don't know what we're talking about on a Zoom session day. Okay, if you didn't read in preparation for this week, that's fine. Please go ahead, in addition to completing the assignments this week in topic 1, please get ahead by reading over topic 2. If you just skim it, that should be sufficient for you to at least have an idea of what we'll be talking about next week. Okay. All right, so this week was all about reading about measurements and experiments. Okay. The reading is divided up into 4 sections. You've got an introduction to physics, where we talk a little bit about what the difference is between principles, laws, models, and theories, and we'll talk a little bit about that tonight. Section 2 is about physical quantities and units. We'll be talking a lot about unit conversions and some tips and tricks about the math to do those conversions. In the third section, we'll be talking about accuracy, precision, and significant figures. If you've taken a chemistry class before this, which I believe most of you probably have, you probably have been exposed to significant figures before. We'll be doing the exact same thing in this course, and we'll give you a refresher tonight. And the fourth section is about approximation, so rounding techniques, estimation techniques to kind of make your life a little bit easier when you're doing calculations. Okay. Each of these book sections has an assignment that's kind of tailored to it. Okay. So for example, the conceptual questions lesson is mostly about the first section of reading. So a lot of questions about principles, laws, models, and theories. You have an assignment for physical quantities and units, which is your second section. You've got an assignment for accuracy, precision, and significant figures, and for approximation, which are your last two sections of the reading that you can see there. Following those, you'll see your topic quiz, which you'll have 2 attempts at and an hour to complete. And you have a group discussion. So remember, group discussion, you have to post a unique thread to the question, answer the question in your own words, make it detailed, and also make sure you respond to someone else's thread in the discussion to get full points for that. And then once you do those things, you will be done with topic 1. Okay. The assignments are not very lengthy. I'll kind of give you a taste of them tonight. But let's go over what you should have learned about this week first. So I'm bringing up the reading right now. Okay. All right. So I'm just going to gloss over some of the more important things that you should have taken away from this chapter. I want to skip to the section where it talks about models, theories, and laws. Okay. A lot of people are very misinformed about what these words mean. So let's go over them. Okay, so the first bolded term you come to in this section, and I'm going to zoom in a little bit so we can read this together. Okay, the first bolded term we come to in this section is a model. Okay, right here. Okay, so I'm going to read this. A model is a representation of something that is often too difficult or impossible to display directly. Okay, they give the example right here, a planetary model of the atom. Okay, so based on the definition, it would be very difficult to display what an atom looks like in reality, because the atom is so tiny, we have really no way of visualizing it. We don't have the technology to do that, really. And also, there's a lot of ambiguity about what the atom actually looks like. There's a lot of controversy and disagreement, even today, about what the atom looks like. So, to kind of simplify atomic structure, we sometimes use the planetary model of the atom. Okay, so the planetary model of the atom, if you remember from your chemistry course, you got the nucleus in the middle, which is kind of like the middle of a solar system. So the nucleus is kind of like the sun of an orbiting solar system. The electrons are orbiting the nucleus. So electrons could be represented kind of like planets at different orbits around the nucleus. And that's kind of a silly example. It's actually not very accurate about what the atom actually looks like, but it's a model. So it's good enough. It serves its purpose in dumbing down what the atom actually looks like, so we can actually talk about it and have some sort of concept about what it looks like. Okay, so that's what a model is. It's just a way of representing something that would be difficult to display directly. Okay, a theory. I think this is probably the most. This is the term that most people have misconceptions about. Okay, so I want you to think about everything you know about the word theory. Okay, when you think about the word theory in science, you probably think, oh, a theory is my hypothesis. It's what I think is going to happen. But a theory is so much more than just a hypothesis or a guess. Okay, so let's read the definition the book gives. I'm going to see if I can reword it. So it says, a theory is an explanation for patterns in nature that is supported by scientific evidence and verified multiple times by various groups of researchers. Okay. I'm going to say it a little bit differently. So when I was taught the difference between a theory and a law, I was taught that a theory tries to explain a phenomenon. Okay. Emphasis on the word explain. A theory tries to explain a phenomenon. So a theory is an explanation for something that is happening in nature. Okay. So when you think about popular theories out there, you've got the theory of evolution, you've got the Big Bang theory, you've got atomic theory, you've got theory of plate tectonics. All of these theories are several concepts and explanations that are summarized under the term theory. Okay. And we'll go over that a little bit more once we kind of contrast that with a law. So once again, a theory explains a phenomenon. A law, on the other hand, okay, the definition here reads, a law uses concise language to describe a generalized pattern in nature that is supported by scientific evidence and repeated experiments. Okay, the way I was taught this, remember that a theory explains a phenomenon, a law states a phenomenon. Okay. So when you think about all the laws that you've heard about in science, you probably heard about Newton's laws of motion. Okay, you probably heard about the law of conservation of mass in chemistry. Okay, so let's talk about Newton's first law of motion, for example. So Newton's first law of motion states that an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by some external force. Okay, it's a very concise statement. It doesn't try to explain the phenomenon that we're thinking about when we talk about Newton's laws of motion. It's just a statement. Remember, a theory tries to explain something. Okay, so let's do a little exercise before we move on from this topic. I'm going to bring it by whiteboard. Suppose we were contrasting the theory of evolution with Newton's laws. Newton's first law of motion, let's say. Okay, Newton's first law of motion. Okay, so the theory of evolution, remember, theories explain phenomena. So when you think about theory of evolution, if you've taken biology before, a couple of things probably come to mind. You've probably thought about natural selection. Okay. In other words, natural selection is basically the term that describes kind of survival of the fittest, that cliche that we always talk about when we talk about evolution. So natural selection is basically the concept that an organism mutates itself randomly and acquires some beneficial trait from that mutation. And that mutation, that advantage that organism now has, allows it to outcompete other organisms of the same species for survival. Okay. When we talk about natural selection and evolution, we also talk about evidence for evolution. We talk about fossil record. We talk about genomes. We talk about geological evidence for evolution. We talk about embryology, for example. Okay. When we talk about the theory of evolution, we also often bring up Charles Darwin and his journeys. Okay. So the main point is, under the theory of evolution, there's a whole bunch of bullet points that we could use to to support this theory of evolution. There's so many things that we could pull into our discussion on theory of evolution to explain how things evolve, okay? So look at that lengthy list of things that I just typed. Now let's look over at the Newton's first law of motion. Remember, Newton's first law is basically there to state a phenomenon, okay? So let's just go ahead and state it. An object at rest will remain at rest unless acted upon by an external force. Okay. Now I didn't type up a list of concepts. I didn't type up or talk about anything that supports that. I just stated it. Okay. So theories explain things. Laws state things. Okay. That's an important distinction. All right. So you're going to go over a lot of questions in the conceptual assignment, which is the first assignment over here. So make sure you know those differences between theories, laws, and models, because you will get lots of questions about them. Okay. I'm going to skip over to the next section. I don't want to take too much of your time up in this recording, but we're going to go down here to physical quantities and units. Okay, so your second assignment of the week is right here. Okay, it's named the same thing as the name of this section we're going to be reading in today. Let's talk really quick about SI units. So read this section if you haven't had the chance to already, because it talks about what standard units are. What I really want to focus on is conversions and using the metric system, okay? So for example, take a look here. This is a very useful table with many different prefixes for powers of 10, okay? So look here in the middle of this table. You'll notice it's very blank compared to the rest of the table. This is where we would expect our base unit to go of what we're measuring. So for example, if I'm measuring length, we measure length in meters. So my base unit would be meters, okay? If I was measuring volume, my base unit would be liters. If I was measuring time, my base unit would be seconds, okay? So my base unit, the middle of this table, refers to kind of the most basic way of measuring whatever you're trying to measure. Prefixes above that base unit describe values that are larger than that base unit. So for example, we have a kilometer, a kilometer, for example. So whenever you put the prefix kilo in front of a base unit, it means we're taking 10 to the third of that base unit. So 1 kilometer is 10 to the third meters, okay? I'm not going to expect you to memorize this table, but be familiar with the ones that are a little bit more popular today. So kilo is an important one to know. We probably will go into mega when we go over topics in next semester's class, but kilo is definitely one you want to know. You want to know these smaller ones. So anything below the base unit is going to be a prefix that stands for a smaller quantity than our base unit. So for example, centi, you've probably heard of centimeters before. A centimeter is 10 to the negative second meters, okay? In other words, 1/100th of a meter is the same thing as a centimeter, okay? You want to get really comfortable with these prefixes and these scientific notations over here, because we're going to be doing a lot of work with scientific notation and with the metric system. If you have more questions on that, please email me. There's lots of good references out there that you can look up as well if you ever get confused. Okay, let's talk about how we use these different things. Okay, so the trouble with science classes here in the United States is that science uses the metric system, but if you've grown up in the United States, society doesn't really use the metric system, do we? So for example, in America, we describe something's weight in pounds, okay? But in Europe, they use kilos or kilograms, okay? And that's just one example of a difference, okay? Another example, we use feet and inches in the United States, but over in Europe, they would use meters and centimeters, okay? So living in America and studying science puts us at a little bit of a challenge because we need to learn to convert between units that we've learned our whole lives and units that the rest of the world agrees on. Okay, and that's where we get to unit conversion and dimensional analysis in the text. Okay, so quick thing. If I asked you to convert 2 feet into inches, that would be a very easy problem to do because a lot of you know that there are 12 inches in a foot. And you could simply times 2 feet by 12 inches to figure out that there are 24 inches in 2 feet. But suppose we were doing a pretty complicated conversion. There's a specific type of math that we're going to teach you to do in this class called dimensional analysis. Okay. If you took chemistry already, your chemistry teacher probably taught you a little bit about dimensional analysis. It is a really helpful tool to use whenever you're doing math and science class. So every calculation that we do in this class, I'm going to try and use dimensional analysis to get you guys used to it. So let's go ahead and do an example. Okay. So I'm going to scroll down to the end of the chapter, and we're going to do some examples from this section. Okay. So for example, suppose we do this example number 5 right here. It says soccer fields vary in size. A large soccer field is 115 meters long and 85 meters wide. What are its dimensions in feet and inches? Assume that 1 meter equals 3.281 feet. Okay. All right. So we are given a soccer field. Its length is 115 meters. Its width is 85 meters. And they want those measurements in feet and inches. Okay. And they even give us the conversion factor. 1 meter is the same thing as 3.281 feet. So it's pretty easy for you to probably do this on your own using just kind of logic or doing this in your head. But I'm going to show you how to do this using dimensional analysis. Okay. So once again, our length of our soccer field is 115 meters long. Okay. So length is 115 meters, and our width equals 85 meters. Okay. And our task is to express the dimensions in feet and inches. That's our task. And the other piece of important information they told us is that 1 meter is the same thing as 3.281 feet. Okay. 1 meter is the same thing as 3.821 feet. Okay. So that's going to be important for us to remember. Oh, and I think I made a typo. It's 3.281. So that was my mistake. 3.281. There we go. That's fixed. Okay. So to do a problem with dimensional analysis, suppose I wanted to convert my length from meters into feet and inches. Okay. So I've got 115 meters right here. Okay, so the way dimensional analysis works is you're going to use conversion factors like the one we were given up here, and you're going to set them up as ratios. Okay, so I know that for every 1 meter, I have 3.281 feet. Okay, now you'll notice I've arranged the conversion factor in a ratio or a fraction. And the reason I'm doing this is because whenever I take a number that I'm starting with, such as 115 meters, if I multiply it by a conversion factor, I'm going to get a new unit over here. But what I want to draw your attention to is that I've arranged the conversion factor in this fraction such that I've got meters on the bottom. That's important because whenever you're timesing a fraction by another number, units that appear on the top and the bottom will cancel, okay? And you'll be left with the unit that's left over, which in this case is feet. Okay, so without even doing any math already, just by setting up dimension analysis, I know that my answer is going to have units of feet, okay? Now let's do the math. Okay, so our calculator says, our calculation says we're going to take 115 meters, we're going to times it by the ratio 3.21 over 1, okay? So I'm going to type in my calculator, hey, what's 115 times 3.281? Okay. Now I am dividing by 1 on the bottom, but dividing by 1 is not really going to do anything. Okay, so my answer that I get when I plug this in my calculator is 377.315. So 377.315 feet. And that's your answer. Okay. Now they wanted it in feet and inches. Okay. So because we know that there are 12 inches in a foot, I need to figure out if I have any inches left over. If I figure out how many, let me put it this way. If I take my answer here and divide this by 12, okay, so if I know that there are 12 inches in a foot, if I figure out how many times 12 goes into this number, so 377.315 divided by 12. Actually, you know what? I am thinking of something else right now, so scratch that. Here's what I wanted to say. Because we've got this decimal on the very end, this 0.315 right here, that's not a complete foot. That's part of a foot. Okay, so if I know that I've got 315 thousandths of a foot, 315 thousandths of a foot, okay, because that's 3 decimal places to the thousandths place, how many inches would that be out of 12? Because I know there's 12 inches in a foot. Okay, so if I'm taking a fraction of a foot, let's figure out what fraction out of 12 inches that would be. Okay, so you probably learned how to do this in your math class. Using cross multiplying, I could do the butterfly method, and I could say that 315 times 12 divided by 1,000 gives me 3.78 inches. Okay, so what that means is that my dimensions of my soccer field's length are 377 feet, okay, because that was a whole number, and then since I had a partial foot after the decimal place, this 0.315 if you remember, if I figure out what fraction of 12 inches that would be, I get 3.78 inches. So my final answer is 377 feet and 3.78 inches. That would be my length of the soccer field. Okay. So that's an example of how you would use dimensional analysis. Really, just remember, setting up the calculation this way so that the units cancel, that's what dimensional analysis is all about. It's really just there to reassure you that you're going to have the correct unit that you're looking for in your final answer. Okay. I'm not going to finish with the width because that's probably something you can do on your own. But I wanted you to be able to see the length portion of this question just so you could see how the dimensional analysis worked. So let's go back to our reading and let's talk about the next topic. Okay. So next up in our reading was accuracy, precision, and significant figures. This is also a topic you probably learned about in your chemistry class if you took chemistry. So I want to talk about some problems you'll see in the homework for this section. We're going to be talking a lot about things called uncertainties. Okay. We'll also be talking a lot about significant figures. Okay. So let's talk very briefly about those two topics. And I want to do this in the context of an example problem. Okay. So first of all, uncertainty comes with any measurement you take. Whenever I teach this to students, I always talk about how if you have a ruler and you're measuring the length of a shoe, let's say, you might measure the length of that shoe to be 9 3/4 inches, 9.75 inches. But you got to ask yourself, can you be absolutely confident in that measurement if you measure something to be 9.75 inches? Is it 9.75 inches on the dot? Is 9.75 inches your best guess as to the length of that object? We really can't be certain about the actual length of that object because our tool could be imperfect. Our ruler could be off by some percentage. Okay. My point is, any measurement in science comes with a little bit of uncertainty. Okay. So you'll often see uncertainty displayed as a plus or minus value. So take a look here where my cursor is. So for example, the length of a paper could be expressed as 11 inches plus or minus 0.2. So what that means is that we think our paper is 11 inches long, but we could be off by 0.2 inches. We could be 0.2 inches over what we're supposed to be. We could be 0.2 inches under what we're supposed to be. So this plus or minus 0.2 is called our uncertainty. It's the error with which we are measuring. Okay. So there's a couple of things that you'll be doing with uncertainties in your assignments this week. So here's an example problem. Suppose your grocery store sells 5-pound bags of apples. You purchase 4 bags over the course of a month and weigh the apples each time. You obtain the following measurements. You've got the weights for weeks 1 through 4 of your 5-pound bag of apples. Okay, so look at what you should be getting. We sell these bags of apples under the assumption that they're 5 pounds each. But when you actually weigh them, some might actually be below 5 pounds. Some might be above 5 pounds. Okay, so keeping on with the question, you determine that the weight of the 5-pound bag has an uncertainty of plus or minus 0.4 pounds. What is the percent uncertainty of the bag's weight? Okay, so if they give you the expected value for what the weight should be, that's 5 pounds in this case. That's what we should get when we weigh it. They're giving us an error of plus or minus 0.4 pounds. Remember, that's what our measuring tool could be off by. Okay, and if they're asking you for the percent uncertainty, it's a very easy calculation to do that. Okay, so let's go ahead and type this out for you. Percent uncertainty is equal to, you're going to put your expected value in the denominator of a fraction. Okay, so expected. I'm going to abbreviate EXP. Okay, so expected value in this case is the 5. That's what we expect the bag to weigh. Okay, you're going to put your uncertainty value in the numerator. Okay, so I'm going to put UNC for uncertainty. And then to convert it into a percentage, we're going to times that fraction by 100. All right, and that's it. That's your equation for percent uncertainty. So in this case, we would put the 0.4 in our numerator, because that's our uncertainty. We'd put the 5 pounds in the denominator, because that's what we'd expect the bag to weigh. We would take 0.4 divided by 5 times the whole fraction by 100, and we would get our percent uncertainty. And you can see them doing this in the solution down below. They get a percent uncertainty of about 8%. Okay. What that means is that plus or minus 0.4 pounds, the error in the scale that you're using, for example, it's off by 8%, either in the positive direction or the negative direction. Okay. So that's how you calculate percent uncertainty. Going on. whenever you're doing calculations using uncertainties, your final answer has to be of a certain uncertainty. Okay, so for example, you're going to be doing some things in your homework with area. So you guys all learned probably in 4th grade that area is length times width, right? So if you have a length and a width that you're given in a problem, and you're asked for area, so area equals length times width, whenever you're trying to figure out uncertainties of problems like this where you have to times things together, okay, we got to use the method of adding percents. So take a look at this definition. The method of adding percents can be used for multiplication or division. So in this case, if we're trying to find the area of this room, 4 meters is how long it is, 3 meters is how wide it is. 4 times 3 gives us an area of 12 meters. 12 square meters, I should say. Okay, 12 square meters. Now, suppose for a second that my length had an uncertainty of 2%, and my width had an uncertainty of 1%. Okay, if I know that information, I can use the method of adding percents whenever I'm multiplying or dividing. So since I multiplied length and width to get 12, by using the method of adding percents, I can take my 2% uncertainty and I can add that to my 1% uncertainty for my width, and I get 3% uncertainty. So that's what I should have as my answer. So 12.0 meters squared plus or minus 3% uncertainty. All right. So just to repeat and to sum it up, whenever you are timesing or dividing in a calculation, you can take your percent uncertainties and add them together. All right. So that's how you do that. Okay. Yep, and right there's the answer right there in the text. Uncertainty of 3%. So good job. You can use the equation we talked to you about 5 minutes ago to convert this percent back into an actual uncertainty. But I think most of your homework problems are going to have you calculate percent uncertainty, so it's pretty easy. Okay, last topic of the night. In chemistry, you probably learned about these things called significant figures. Basically, significant figures are the number of digits we are allowed to have in our answer based on the measuring tool and how imperfect it is. Okay, so for example, if you're a football announcer, and if you've ever listened to football announcers talk about like where the ball is placed on a football field during a game, they don't say something like the ball landed at the 35.05 yard line. Okay, they just say the ball landed at the 35-yard line. Okay, and the reason they don't go more precise than that is because they are up above in the announcer's box. They can't really see that well onto the football field. So they have to, there's a little bit of uncertainty in their measuring of where the ball is. So they're not allowed to go that precise because they're not confident in that measurement. So they have to keep it simple and say the ball's at the 35-yard line. Okay, it's the same kind of thing with science. When you are taking a measurement, you're only allowed to report digits that you are confident in and an additional digit that you're not confident in. Okay, let's talk about the homework problems though. So take a look at this practice setup here. I'm gonna try to make this as simple as I can. Whenever you're asked for sig figs or significant figures, suppose I ask you how many significant figures are in this number right here. Okay, any digit that's not a 0 is always going to be significant. So this 9, it's not a 0, so it's going to be significant. each and every time. So I know that the 9 is significant. Okay. Let's talk about the zeros though. Any zeros that come in front of a non-zero. So you see all these zeros that are before that 9. We call them leading zeros because they're in front of the 9. Okay. Leading zeros are never significant. Okay. So in this example, there's only one sig fig. There's only one significant figure. It's the 9, because all of the zeros before it, they don't count. Any leading zero never counts. And the reason why is because those zeros are just serving as placeholders. Okay? Let's talk about the next example. You'll see here in this case, we've got not leading zeros, we've got trailing zeros. They come after the numbers that are not zeros. So if you're counting significant figures, we've got 15450.0. The 1545 are non-zero, so those are automatically going to count as significant. Do trailing zeros count, however? And the answer is it depends. Okay? Here's the rule of thumb. If you can see a decimal point, like we can in part B, if you can see a decimal point in the number you're given, every trailing zero counts as significant. Okay? So in part B, if I'm asked how many significant figures are in that measurement, I would say, well, I count 6 significant figures. Okay, the reason I'm getting 6 is because I've got 1545. I've got 4 digits there. They're non-zero, so they're automatically significant. And because I've got a decimal point, those 2 trailing zeros at the very end of the number also count as well. Okay. Let's talk about part E for a second. You'll see here in part E, we've got non-zeros. We've got 3, 4, and 2, which are not zeros. So those 3 digits are going to be counted as significant. And we've got this 0 that is sandwiched in between the 3 and the 4. Whenever you have zeros like this that are sandwiched in between non-zeros, those will always automatically count as significant. Okay? So there are 4 digits that are counted significant in this measurement. Okay? All right. We are running out of time, so we got to get going on to our last concept. Whenever you're doing calculations with significant figures, there's 2 rules you need to follow. Whenever you are multiplying and dividing numbers in science class, your answer should have the same number of significant figures as the quantity having the least significant figures entering into the calculation. So for example, take a look at this example down below. I'm timesing pi by the square of a much less precise number. If you look at the pi value they give, 3.1415927, that's got about 8 significant digits in it right now. That's a lot. You're timesing that by a value that only has 2 significant digits. The 1.2 only has 2 significant digits, whereas pi over here had 8 significant digits. So the rule says my answer can only be expressed to the same number of sig figs as the least precise of the 2 that I started with. So this 2 right here, that's the lesser of the 2. So even though my calculator is going to spit out a long answer at me, I'm only allowed to keep 2 significant figures. So I have to round my answer to 2 digits. Okay, that's the multiplication division rule. If you're ever adding and subtracting, the answer can contain no more decimal places than the least precise measurement. Okay, simply put, if you're adding or subtracting numbers, you got to count decimal places. So take a look at this example. In 7.56, I've got the 10th decimal place. I've got the 100th decimal place. That's 2 decimal places. So 2 dp, let's say. dp means decimal places. 6.052, I've got the 10th place, 100th place, oh, excuse me, the tens place, the hundreds place, and the thousands place. So I've got 3 decimal places. And then the last value, I've only got the ones place, or the tens place, excuse me. So I've marked how many decimal places there are off to the side here. The rule says my decimal places can only match the least precise of those measurements. So I'm going to look at my least precise. My 1 decimal place value is the least precise, so my answer can only have 1 decimal place in it. Okay, so even though my answer gave me 5 digits, I have to round it so there's only 1 decimal place. And that's how they got 15.2. Okay, all right. I think we are done. We're running out of time. So that should give you at least a couple hints about how to do the homework for this week. If you have questions, please email me. Work with your classmates, but please don't plagiarize. And as we mentioned in last week's tour video of the class, you have to show all your work in your homework submissions. So you can do this by scanning pictures into your assignments. You can type out the calculations yourself, which doesn't take that long, but make sure you show all your work. All right, once again, I hope to see you in class this week, but if the hurricane has other plans, hopefully this video will at least get you through until we can see each other. Thanks a lot, good luck, and have a good week.